In this lecture, we will see properties of scattering parameters. The second tool that we have introduced, or now this is the first that obviously Z matrix, impedance matrix is a popular tool. So, this S parameter is related to Z like this. If you know Z matrix, you can find S parameter. So, that means any lumped network, if you know its Z parameter, you can always find its S parameter. We will see in one problem, we will give a lumped network. So, if you want to find its S parameter directly, that may be a problem, because for lumped parameters the separating incident, reflected, transmitted voltages, that becomes a problem. So, there Z parameter finding is easier, you can do that and then come to S parameter. On the other hand, this we have said that the second equation, that is, if you know S parameter, you can find Z. Now, for microwave networks, this is helpful, because in microwave networks you see that it is easier to find out the reflected, transmitted and incident waves. So, their ratios is easier to find. You find S matrix, then find the Z matrix. So, suppose a transmission line is given. Now, its S matrix is easier to find, but if you want to find Z parameter of a transmission line, first find S parameter, come to Z parameter by using this equation. So, these two relations help, and once you know Z, you know there are relations between Z and Y. So, if I know Z, I can go to Y. Also, there are relations between Z and H. So, if I know Z, I can go to H. Also, there are relations between Z and ABCD. So, if I know Z, I can go to ABCD. So, with these two, you can go from one to others. So, our advice is, if a lumped element is there, not a distributed one, try to find its Z or Y, whichever is convenient, then finally find Z, and if you want to find S, from Z use this formula to find S. On the other hand, if there is a distributed line, then try to find its S parameter, and from S parameter you can come to Z or Y as required. Now, various times we see that a network is reciprocal, mainly if we do not use any non-reciprocal device. One of the very popular non-reciprocal device is ferrite. So, if ferrite is not used, or other such non-reciprocal special materials not used, in most of the passive devices they are symmetric or they are reciprocal network. If they are reciprocal, the scattering matrix that becomes symmetric. Now, symmetric means what? That S and S transpose, they are equal. You see, you know a matrix, I can take a transpose of the matrix. So, for a reciprocal network, S and its transpose is same. So, we can easily check whether if we know S matrix of any network, particularly with network analyzer, we can find out S matrix, we can easily check whether it is a reciprocal network or not. Now, if a network is lossless, lossless means there is no dissipation of power there, whatever is entering inside there is no loss, that is called a lossless network. So, for a lossless network, the S matrix is this property. You see, S conjugate is equal to S transpose inverse of that. Now, if you remember, any network whose conjugate is equal to inverse of transpose, that is called an unitary matrix. So, for a lossless network, S is unitary matrix. Now, if for any unitary matrix, the elements are related like this: Ski dot Skj star is delta Ij, this delta is Kronecker delta. That means, when Ij equal to 1, this delta becomes 1. If Ij not equal to 1, delta becomes 0. Now, this can be broken into two parts. One is, you see, Ski dot Skj is equal to 1. So, that means any row, any column of Ski means k is equal to 1 to n means any column. So, S matrix, any particular column, if it is dotted with the conjugate of the same column, will get 1. Any column conjugated with the same column will get 1. Any column conjugated with the other columns, that will give us 0. So, for unitary, both these conditions should be simultaneously satisfied. If any of them is violated, it is not an unitary matrix. So, for an unitary matrix, Ski dot Skj star is equal to 1 for I is equal to j. So, this condition, there should be an additional qualification necessary here. Ski dot Skj star is equal to 1, I is equal to j. That means, the same column you dot with conjugate of the same column, you will get 1, and any column conjugate with other column. So, suppose I have S11, S12, S13, S21, S22, S23, S31, S32, S33. Now, the first one says that this is a column, this column. So, if the matrix is unitary, I will get S11 star plus S21 star plus S31 star is equal to 1. S11 star means what? S11 square plus S21 square plus S31 square is equal to 1. Also, I will have for these, that means S12 square. So, this is 1, then I should have S12 square plus S22 square plus S32 square is equal to 1. Then S13 square plus S23 square plus S33 square is equal to 1. Also, this is the first property, that means, for unitary I will have these 3 equations. Also, I will have 3 more equations, that one with the other So, when this will be 0, this will be 0, that means S11 S12 star plus S21 S22 star plus S31 S32 star, this will be 0. These two column, one column conjugate with other column, these are different columns. So, that is 0. Then this one with conjugate of these S11 S13 star plus S21 S23 star plus S31 S33 star, this is 0. Also this one conjugate with this one, that means S12 S13 star plus S22 S23 star plus S32 S33 star is equal to 0. So, to be unitary, these 3 and these 3, the 6 equation needs to be satisfied, then we will say the matrix is lossless or unitary matrix. So, in lossless network, its scattering matrix satisfies all these equations. So, that we are saying the dot product of any column and the conjugate of the same column is unity, dot product of any column and the conjugate of a different column is 0. So, both the things should be simultaneously satisfied. If any of them is violated, it is not a unitary scattering matrix, that means the network is not lossless. Suppose if we have a resistive network, obviously you know resistance creates dissipation of power. So, that matrix cannot be lossless. So, if any you have resistance used in the network, you can see that its S matrix cannot be lossless. A and B holes. So, now if lossless as well as reciprocal material network, that case the property holds for rows as well as columns, because for reciprocal the network and its transpose is same. You know columns after transposition becomes rows. So, here this property holds for columns. Now, for reciprocal rows also will have this. Rows means this conjugated with this row will be 1, this conjugated with this row will be 1, this conjugated with this row will be 1, this conjugated with another row will be 0, this conjugated with another row will be 0, like that. So, all these are required when we try to solve various particular networks. These properties helps us to find out this thing, these very useful properties. Now, we come to another thing, that let us see in a 2-port network we have S11, S12, S21, S22. And what is S11? S11 is V1 minus by V1 plus when V2 plus is made 0, match load. Now, is S11 equal to reflection coefficient? In general, what is reflection coefficient of port 1? Reflection coefficient of port 1 is V1 minus V1 plus, but S11 is V1 minus by V1 plus with the added condition of these. So, we can say that if port 2 is terminated in match load, then only reflection coefficient and S11 are same, otherwise they are different. S11 is under this condition reflection coefficient is general. That is why we are saying that in general they are different, that is why the first answer is no, and second answer is yes only when all other ports are matched. then S11 and reflection coefficient same. Generally, it is a misconception, many times people interchangeably say this, but you should remember that under only this condition they are yes, otherwise they are two different entities. Is SNM is transmission coefficient? Again our answer is yes or no. So, it will be yes when it is transmission coefficient from port M to port N when all other ports are match terminated. So, this match termination is important, other ports match terminated, then S parameters S and M are transmission coefficient. So, in a two port network, if I say that is S21 transmission coefficient from port 1 to port 2, the answer is yes, if you have made the S, the second port 2 port is match terminated, that means again V2 plus is equal to 0. If you make V2 plus is equal to 0, this means port 2 match terminated. Then S21 is transmission coefficient. So, a network analyzer measures S11, S21. Now, remember that they are in actual cases when the terminations are different in port 1 or 2, based on that there can be some other reflection coefficient. Only when a port 2 is matched, then S11 is reflection coefficient. Similarly, for S21, only when port 2 is matched, S21 is transmission coefficient. Now, S parameters are properties of network, they are characteristic of network. So, S parameters do not depend on port terminations. If you change the port terminations, S parameters do not change. As we said that reflection coefficient may change, transmission coefficient may change, they depend on port termination. But S parameters are network property, they are not dependent on excitation of anyone. So, they are invariant to port termination, port excitation does not do. Think similar concept that when we say Z parameter, it does not depend on what voltage I apply at which port. It is a property of the network. It does not depend on excitation or response at the ports. Similar thing here. Now, one thing that we have seen in the first lecture today, that in general for at microwave frequency with waveguide type of things, we cannot define voltage uniquely, but under certain restrictions we have defined. But that definition we that time said is only at a particular terminal plane, at a particular port I can define uniquely a voltage or current. So, voltages are defined at ports, S parameters are also port dependent. Now, if I change that port, that means if I extend that port, that terminal plane, I can extend, then I need to redefine the voltages and the S parameter will also get changed. So, that means, see in this case that I have a network, I had the ports here, port 1, port 2, port 9 etc. It is an n port network, the S parameter is S. Now, suppose I extend the port and put that instead of this plane, I say this dashed plane here, that means I have extended the port. So, definitely this V1 plus has been changed here, V1 plus dash etc. So, S parameter of the whole thing will be changed and that new thing we are calling this S dashed. Instead of S, with respect to this new ports, it is S dashed. Now, what is the relation between the two S? suppose this extension is every port I extend by an electrical length of theta. You know that basically it is a transmission line. So, they are for a lossless transmission line of electrical length theta, that means if physical length L, electrical length is theta, the relation is theta is equal to beta into L. So, this electrical length of this one is theta. So, the S dashed, the new S parameter, that will be given by this, that port 1 is extended by, let us say, or theta, they are calling phi. So, phi 1, then port 2 by phi 2, etc. So, you write the matrix like this, then S, then again this. So, this will be your new port definition. So, S dash and S are related by this. This is called port extension. And another thing is that various ports, now we define parameters. Now, let us say that characteristic impedance of various ports are different. This thing happens, suppose many times we write, suppose in a waveguide there are 5 number of modes going. So, we say that it is a, though there may be a single port there, but we say electrically it is equivalent to 5 different ports, and each mode may have different port impedances. So, this is the how to write generalized S parameter when the various ports has various impedances. One is Z naught 1, Z naught 2, Z naught 3, etc. So, port characteristic impedance are unequal. In that case, what we suggest that you redefine the voltage, the positive going voltage and reflected voltage, that means incident voltage V n plus, you divide it by root over impedance of the port, and that let us call A n. Similarly, the reflected voltage from the port, nth port, that you divide by the square root of impedance and call it B n. And instead of V 1 plus V 1 minus, let us say that A 1 B 1 are the equivalent voltages. They are hypothetical ones, this A n B n, A 1 B 1, A 2 B 2, etc. So, beauty is here, if you write now V n, the total voltage here, that will be dependent on root over Z A Z 0 1, Z 0 n, I n will be also dependent on Z 0 n, P n also dependent on, you see that in the P n expression there is no impedance coming. So, voltage current there in this new generalized thing, they are impedance dependent, but power is not if you write it in terms of A n, but if you write it in terms of V, it will be power will be dependent on impedance as well. So, power independent of port impedance, generally this power is the thing that is required in many cases. So, if you want to make power expression independent of port impedance, this generalized S parameter A B can be used. So, V n I n depends on port impedance. So, you see that S I j depends on port impedances, but in terms of B A there are no impedance coming. This is one advanced concept, just we are mentioning because we are introducing S parameter, that if you have various port A thing, you can write it in terms of this A B, but this generally in simple cases you do not require. This is when in a particular guide various higher order modes are travelling, you can use this generalized scattering parameter A B instead of V plus V minus. all we had in this properties of S parameter. So, we have seen properties. Now, in the next lecture, we will see the instrument network analyzer, that what it does and how it helps to find out S parameter measurements. Thank you.